All right, so taking a look at this, it's called an isocyanate molecule. You don't need to know that. Has this carbon in the middle that's sp hybridized, right? Because it has 2 pi bonds. And the question here, they're asking for draw a significant resonance contributor for the following compound. So what you need to do here is, what's a little strange is that you have an oxygen and a nitrogen and a carbon. Oxygen and nitrogen are certainly more electronegative than carbon, so you know you're going to probably push electrons towards those. The thing that's going to be different here when you have this kind of arrangement, this kind of an sp hybridized carbon in the middle, the lone pairs of these nitrogen and oxygen actually can be in p orbitals. So this is just a weird situation, like a particular situation. We have this sp carbon in the middle, so this nitrogen can actually choose to be, right, it's already sp2 hybridized. It's going to take even the one more step further and decide to be sp hybridized. When it decides to be sp hybridized, this lone pair then can go into a p orbital. The oxygen could do the same thing. The oxygen, right, we look at this and we'd say that oxygen's sp2 hybridized. But because it's right next to this other pi bond, right, again, the situation where this carbon, right, it looks like this, this oxygen can actually decide to be sp hybridized as well. So one of these lone pairs is in a p orbital. So let's draw the two. Let's think about who's more likely to give up electrons, nitrogen or oxygen. Nitrogen. Why? Because it's less electronegative, right? So let's do that. Let's move those electrons and see what this could look like. Let's number our carbons, elements, 1, 2, 3. So I'm going to move these lone pairs to form another pi bond. As I do that, these lone pairs are going to go to the oxygen. Resonance arrow. All right, so I generated a new pi bond. This oxygen got another lone pair. Now I need to make sure I balance my charge. Overall, what was my net charge of my starting molecule? The isocyanate, it was a neutral molecule. So who has a plus charge, who has a minus charge then? Plus on the nitrogen, and negative on the oxygen. Right, so this is one of those weird kind of special situations where, right, I look at this and I say sp2 hybridized for sure. But it could be sp, right? Just like we said, if something's sp3 hybridized, it could take a step back and become sp2. Same as really, I mean, it's rarer, it doesn't happen as often, but you can be sp2 hybridized and say, oh my gosh, I'm going to go become sp hybridized now. It's rarer, but it can happen. So this is kind of, right, if you kind of looked at this, right, you would like, this is like an allylic system, right? A little bit, but it's different, right? It's kind of a special situation. This is not like any of those 6 things I showed you from the textbook. This is like a really particular special kind. So this is a sapling question, and when they've drawn methanol several different ways. So I'm showing the first kind of interaction, and they're saying there's several proposed intermolecular bonding interactions are highlighted in green. If a highlighted interaction is a valid hydrogen bond, leave it unaltered. So basically they're asking you to say here's methanol. How does methanol hydrogen bond with itself? What's that interaction look like? And of course, this is all based on opposites attract. So first thing you gotta do, let's just look at methanol itself. Methanol itself, let's draw on some lone pairs. That might be helpful to understand this. It's kind of asking is, do we understand polar bonds and polar molecules? So here we have methanol. Where is methanol electron rich? On oxygen, specifically on its lone pairs, right? The electrons are electron rich, right? The electrons are electron rich. Where is methanol electron deficient? Where is it delta plus at? At the hydrogen, that's right. So for 2 methanols to interact, you want one part of the methanol, the electron-rich part of the methanol, to interact with another methanol's electron deficient part. Right here, what is this? If an H and an H are bumping into each other, is that going to work? No, because this is electron deficient and that's electron deficient. That's not hydrogen bonding. So this would not be this would not be an interaction, a hydrogen bonding interaction, right? So basically this is saying these molecules exist somewhat in 3 dimensions. They got to kind of orientate themselves to actually have these hydrogen bondings take place. It can't just be that 2 molecules always come together perfectly. So what about one, let's look at one that is an actual hydrogen bonding interaction. So now look what's different here. You see how, in this case, the lone pairs from this methanol are lined up, kind of orientated so they can be close to the hydrogen from this methanol, and the hydrogen from this methanol is closer orientated towards the lone pairs from this methanol. Right? So for the hydrogen bonding interactions to take place, you have to have the electron density of one molecule be interacting with the electron deficient part of another molecule. Right? And this is hydrogen bonding, so specifically it's a heteroatom interacting with a hydrogen from another molecule, right? Intermolecular forces, right? Hydrogen bonding between things. So now let's take a look at these two. Is this showing a hydrogen bonding interaction? Is the electron-rich part of one molecule interacting or lined up with the electron-deficient part of another? I think so, yes. Right? Right here. Right, where the electron-rich part of this lone pairs is lining up with the H from that methanol. It's not 2 interactions, not 2 hydrogen bonding interactions at once. It's just the one, but it's still a hydrogen bonding interaction. All right, so taking a look at a condensed Lewis dot structure. This is a condensed Lewis dot structure. How do I turn this actually into something with bonds and connectivity? First thing you could do, right, the tricky part is these parentheses. These parentheses become tricky. The parentheses are saying there's 3 CH3s bonded to one of those carbons. There's 2 CH3s in this case bonded to one of these carbons. The question is, which carbon is it? So there's a couple tricks you could do. I always think it's a good idea to number carbons. All right, so let's number maybe these carbons in the middle. 1, 2, 3. And the reason I numbered those is just because we're used to kind of having, right, you could probably draw, you know that these are bonded together, right? Maybe you know that. You're kind of confused maybe by the parentheses. Now, is this carbon number 1 like for naming? No, I just arbitrarily did 1, 2, 3. So this has nothing to do with naming. It's just me giving those numbers. So I know carbon 1 is bonded to carbon 2, right? And carbon 2 is bonded to carbon 3. Right, carbon 1 is bonded to carbon 2, CH2, which is bonded to carbon 3. Let's put those numbers in. 1, 2, 3. Now, don't forget, how many bonds does carbon want to have? 4. So let's just go ahead and draw in, right, those bonds. So carbon 1 needs to be bonded to 3 things. Well, what else is carbon 1 right next to? This parentheses CH3 with 3 things. So each one of these CH3s, there's 3 of them, are bonded to carbon 1. Let's put those in. What about what's left? We're missing 2 bonds here. There's another parentheses, 2 CH3s. There's 2 of them. They must be bonded to carbon 3. All right. Now you could take this and shrink it down. Or if I shrink that, how can I draw this as a line bond structure without the hydrogens drawn in? That was 1, 2, 3. So that's the other way they ask you to draw it too. Parentheses can be tricky. That's a good little trick there. All right, so a naming question. If you see something like this, at least for me, it's hard. I have a hard time looking at this and finding the longest parent chain. So I like to take this and then and turn it into the stick kind of models. All right, so I think I transferred that correctly. So I just have a hard time looking at this. For some reason, this looks better to me. So what you need to do here, you need to find, so it's an alcohol. So you have to have the longest parent chain with the substituent in it. The longest parent chain with the substituent in it. So you know you have to have the alcohol. So you either you want the alcohol to have a low number, hopefully. But I would kind of start from one of these places. So I would say 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. Same. 1, 2, 3, 4, 5, 6, 7. That's the best so far. 1, 2, 3, 4, 5, 6, 7. Okay, so it looks like I have two options. But I'm starting from this side, and I'm going either 1, 2, 3. So I think I know for sure. This is carbon 1. This is 2. This is 3. And this one's 4. Now the question is, do I go this way or do I go this way? Right? Let's see. If I go this way, I don't really know how to name this. Well, one thing I wouldn't ask you this kind of question, right? If this was 4, then you'd have this piece down here. It'd be actually an isobutyl, which you don't know how to name yet, or you probably will never know how to name. So the best way to go would actually be this way. It also gives the lowest substituent number. The way this question was given, it was just a multiple choice as well. So if I keep doing that down that line, 5, 6, 7. So there's my parent chain. So it's a heptanol. It's a 3-heptanol. What else do I have on it? So I have heptanol and I have a 1, 2, 3 methyls. So it's a trimethyl, and it's 3, 4, 6 trimethyl. I have a 1, 2, 3 propyl group on there, and that's at carbon 4. And which comes first, M or P? M. So it'll be not one. It'd be a 3, 4, 6 trimethyl, 4 propyl, 3 heptanol. So it's a 3, 4, 6 trimethyl dash 4 propyl dash 3 heptanol. Heptane spelling is not my strongest suit. Heptane. No.